All right, thanks everyone. Thanks again for joining us today. Again, my name is Kevin, and I'm joined today by Guillaume Morin, who's going to be co-presenting with me. And we're really pleased to have you with us. The topic for today's webinar is analysis-ready data workflows to support open data cube time series analysis. So just a quick introduction, myself on the right. So I'm the Director of Marketing at PCI, and Guillaume is also here. He's the GXL Delivery Lead, and he'll be presenting a live demonstration and has really led the integration and exploration of the data cube within PCI. So he's a great resource to have here with us, and I'll be handing over the mic to him a little bit later on. Just some logistics, pretty standard stuff. So the lines are muted. So if you're in a room with other people, don't worry, you can talk and discuss what we're showing. It's not going to disrupt anybody. If you have any questions, we really encourage you to ask them throughout the session. So just type them into the questions panel. If you do have a problem or anything like that, you can let us know through the chat. And if you have audio on your computer, we will do Q&A session at the end. So if you actually want to speak to us, we can unmute your line, but otherwise your line's going to be muted automatically. We are recording this, but that doesn't give you a reason to leave. Please stick around. We like the interactive part of these webinars, and we look forward to getting a lot of questions from you. So we always like to make these webinars interactive and engaging. So we would first like to poll our audience and get a little bit of a sense of how you currently use imagery. So just to get a sense of our audience, are we, are people attending this webinar just kind of getting us started? Are you working just with a few images? Are you doing advanced, maybe object-based image analysis? We're just trying to get a gauge of what type of imagery you're working with and what kind of analysis you're doing. And if you have some insights in terms of what you're doing and what you're interested in today, by all means, type that into the questions panel and let us know. So I'm going to leave that open just for a few more seconds, and then I'm going to shut it down. So, so let me shut that down in 3 seconds. 3, 2, 1. Thanks very much. So I'm going to close down that poll, and looks like a lot of people are doing pixel-based image analysis. Some people are doing manual work, and a few people are doing object-based image analysis. So we presented a webinar last month on object-based image analysis, so I apologize. I think the question is a bit of a leftover from that webinar, but still very useful for us to gain insights. So let me get started with the content. So one of the key things that we've noticed in our industry, I'm sure all of you who are here today are familiar with the remote sensing industry, and this was a great article put out by the European Commission and the JRC back in 2014, showing the frequency of satellite launches, sort of who were the first and the second and the third, so you can get a sense of, the US being the first country, Russia, India, France, Japan, and so on, as you work your way towards the right. And then what you see is just the sheer number of countries that are participating in Earth observation remote sensing is increasing. In 2017, according to this report, we're up to 35 countries participating, and a total of 178 optical and 19 SAR satellite launched over the course of the last few decades. So there's just increasingly more and more data, more countries launching satellites, and this, of course, is a fantastic development in our industry. It's a very exciting time to be in the remote sensing industry. There's just lots of data to work with. Of course, this creates challenges, and that's why we're talking about the data cube today and the possibilities of addressing some of those challenges and dealing with all of this these large data sets. So it's great that there's all this data. This data is varied in terms of resolution, in terms of spectral bands, in terms of ground coverage. It's very different data to work with, and so bringing it all together and being able to work with all of that data is, of course, of key interest for a lot of scientists and operational organizations around the world. Now, one organization that has really been critical in terms of addressing this big data challenge that we really want to point out today is Geoscience Australia. Geoscience Australia began an initiative going back about 5 or 6 years, known as the Australia Geoscience Data Cube. You can see some visuals here from their website. And what they did was pretty impressive. They developed an infrastructure by which to ingest and manage and store just huge amounts of data, in this case Landsat data. So every single Landsat image collected, I believe from the 1980s all the way to present day, into this data cube structure that was created by Geoscience Australia. And really what that permits then is to remove the requirement to pre-process data for a specific area of interest on an individual basis when you're studying a particular problem, and create an environment where all of this data could be stored in a data cube, and then the user can then ask the questions that are of interest to him or her. So they could be related to water extents over a period of 30 years. They could be related to vegetation differences over a period of 30 years. So really what this initiative allows remote sensing professionals around the world to do going forward is to really explore the data to its full potential. So we're really excited to see this development, and we're fully participating with organizations around the world, including Geoscience Australia, to make this an operational reality. We see PCI playing an important role to allow users to operationalize some of this technology. So we're very excited to be part of this. The Open Data Cube is something that has evolved out of the initial work from Geoscience Australia, and it's been adopted by the Committee on Earth Observation, or CEOS, and really it sets a standard for creating a data cube and also sharing the code through open source software initiatives. So we're going to be showing an actual CEOS data cube today. So Guillaume has downloaded the source code for the CEOS data cube, and that's what he'll be showing you today. Now, the Open Data Cube addresses these key buzzwords that some of you are probably familiar with. When we talk about big data, whether it's in the defense industry or in solving the human genome or any big data problem, we talk about the 5 V's. The 5 V's are volume, velocity, veracity, and variety. And this is directly extracted from the scientific article, which I'll give the reference in a minute, that was published by Dr. Adam Lewis and several other colleagues that are listed on that paper. And what the data cube allows to address in terms of big data are the following. So in terms of volume, by storing surface reflectance, pixel quality, and other products in the data cube, and high performance computing environments. So really you can address the sheer volume of the data by leveraging the data cube architecture. The velocity, so because you can work on such a much smaller scale, you do have access to all the data, but when you're querying the data, you can handle the speed at which the data can be processed. So if you're getting new collections from all these different sensors, you can query the data very rapidly using these high-performing computing environments and also the data cube infrastructure. In terms of veracity, so how do we know what we're looking at, the traceability of the pixels over time? What we can do through the data cube infrastructure is we can create, manage, and store all the Earth observation metadata using adopted standards. For example, the Open Geospatial Consortium, OGC, would set standards that can be followed to store all of this data and to be able to verify where the change occurred and from where it occurred. The variety, this is a key thing. We're going to be showing Landsat and Sentinel, but as you saw in one of my first graphic, the sheer types of different sensors, it really creates a problem. So the normalization of the data to surface reflectance allows us to bring all of that into a common environment through the preparation of analysis ready data, surface reflectance, as mentioned. Now, Dr. Lewis did not mention value, but I'd like to point it out. Clearly, the value in doing this is to leverage all the data in the archives. So scientists that are attending this today, or operational organizations that are attending this today, tend to focus on small areas and do what we refer to as a pixel torture or detailed analysis over a very small area with a very small data set. The data cube allows you, because of its infrastructure, to really ask questions that you've never been able to ask. So we think that's a fantastic value of using this type of technology. Here are some results. So why would you do this? So here are some results from Dr. Lewis's paper. This is an example of a high tide composite. So going back to 1987 all the way to 2015, looking at the changes in tide over time and being able to create the composite image on the right. So the low tide composite image on the right, and then the high tide composite image on the left. So this gives you high tide, low tide, maximum extents over a period of several decades. So this is an example of a product that you could ask over this small geographic location very quickly through the use of the data cube. Another example here, so this is another query that can be performed leveraging the data cube. This is looking at water observation from space, and you can see the river network and showing the extents of flooding over time. So the colors are indicating the frequency of inundation and the range or the spatial extent of the inundation over time. So you can get a sense of the spatial extent and the temporal frequency and location of those floods over time. And this is the reference paper. If you simply Google Dr. Adam Lewis and Australian Data Cube, you'll land on this. It's an open paper. You can download it. It's a very interesting paper. Encourage you to read it. So what are the requirements for doing all of this? This is fantastic work, and it requires some things. So we've been busy thinking about this over the last few years, and we just want to kind of discuss a little bit what are the requirements. So one of the first things is to create analysis-ready data. So it's a pillar. It's one of the 3 pillars of doing this type of analysis, this ODC time series analysis. The analysis-ready data really requires 2 things. It requires super registration. So if you're collecting images from different viewing angles or different sensors and you want to compare them over time, you want to be absolutely certain that the spatial location of each pixel is as accurate as possible. So that's of critical importance. The other critical important item of interest is the radiometric normalization. So if you're looking at changes over time and you're possibly attributing that to the fact that you haven't processed the data the same way, then obviously that's going to create a problem in your analysis. So when Dr. Lewis talks about surface reflectance and normalization of the data, that's critically important. So this is the main pillar that relates to creating analysis-ready data. The second pillar is, of course, the open data cube itself. So this is the infrastructure, the database that stores the data, everything that allows you to basically do small studies over smaller areas, and then to scale that out to a larger data set, to a larger population of a big data set, as has been done in Australia. So you could see that all of the Landsat data over the entire continent was made available in the data cube. Scientists were able to use that to query specific locations and then get those answers across the entire data set across all of Australia. And really the platform, the architecture that's there, the fact that it's been shared through open source initiatives makes it possible to replicate this environment. So we've done that here at PCI, and Guillaume's going to be showing that. And you'll see also, as you look into this topic, you'll see that other countries have adopted the Open Data Cube as a standard to create their own data cube initiatives on a national basis. So Colombia has a data cube, Switzerland has a data cube. Many countries are adopting this as a standard. So it's very exciting to see this develop. The other pillar, the key pillar, is what we call multi-temporal analytics. So the ability to interface and query your data set over small areas where you know that there are dynamic phenomena occurring that you want to study at a larger scale or at a continental scale. You want to be able to have an environment where you can do that. So you need some kind of an interface to query over small areas and to prototype. So what we'll be showing you today is some pre-configured queries that are built into the CEOS data cube, but you could develop your own algorithms. So for example, if you had a specific algorithm to detect a particular type of vegetation in a particular environment, you could code that using open source libraries or using PCI technology or whatever technology you're comfortable using with. And then you can bring that into the data cube and replicate on a much larger scale. So these are the three key pillars that we see as being critical to doing open data cube time series analysis. There's some other things that are very interesting that we think we can add value to. So one of the things is pen sharpening. So as you probably know, the ability to bring spectral information down to a higher resolution is of interest. So that's what pen sharpening is. And previously, techniques that have been used by ourselves and other people in the industry and have achieved the increase in spatial resolution at the expense of reducing the quality of the spectral information in the data. So although you're able to make a pretty picture, a nice looking image at high resolution with the spectral bands, you have limited ability to use that spectral information at the higher resolution to do the quantitative analysis. So PCI has been busy developing a multi-resolution analysis fusion technique. It uses wavelet techniques for preserving the radiometric quality of the data and the spectral information. So you'll see in a few minutes some of those results. So we think this is a great addition. So for example, Sentinel image, which provides 10-meter data, could be pan sharpened using this MRA and has been in this example pan sharpened to 10-meter resolution. Here's an example of what I just discussed. So on the left, what we see is what's supplied from the vendor. So this is, in this case, this is coming off the Copernicus distribution center. So we have 60-meter data, we have 20-meter data, and we have 10-meter data. Of course, we can we can use those at the different resolutions, but using pan sharpening and the MRA fusion technique available within PCI, we can bring all of that data down to 10-meter resolution and use that. So really that's going to enrich the quality of the results that you can achieve with the data sets. Here's an example of geometric. So we can fuse the data, get it down to a higher resolution. This is another example of Copernicus data, so Sentinel-2 imagery distributed over the same location. So we have 3 different locations and 2 different dates. So site 1, site 2, and site 3. And you can see there's a bit of a shift. And if I go to the next slide, you'll see that using our super registration algorithms within PCI technology, we can bring those data sets into perfect alignment. Another example, this is a data set from Planet on the left, and we just saw this come across recently over social media a couple of weeks ago, and it's an interesting location. It's over Libya, and it's showing some development of some oil pads. And hopefully this is coming across through the webinar, but on the left, what you see is things are shifting around a little bit from left to right. You can see some of the roads shifting, the perimeter of this industrial facility shifting around. And on the right, what you see is the same data set that's been processed through PCI's technology to achieve that super registration, to get things down to 1/10 of a pixel accuracy, to be certain that when you're comparing these images and you're looking at changes over time, what you're seeing are real changes on the ground, not changes in the registration. So that's, of course, very important. A couple of other things. So cross-sensor calibration. When we are comparing different data sets, which is possible, of course, we need to normalize the data. Here we have a PlanetScope image of December 1st collected at 3 p.m. And I'll just toggle to the next image, which is December 3rd, so roughly 2 days later. And we can see that the data sets look similar, but if we were to apply NDVI analysis on that data set without doing normalization, we would get some differences that maybe aren't due to what's actually occurring on the ground. So so this is the NDVI from the first image, and this is the NDVI from the second image. And you can see that those fields brightened up quite a bit. Now that's probably not due to the actual changes on the ground. It's due to the fact that we haven't normalized the data to surface reflectance. So it's critically important to do that. Now, if I show you the same NDVI maps, so this is a normalized data set with the same lookup table applied to both data sets. So December 1st, you can see all these nice green fields. And then if I go to the December 3rd image, those green fields are pretty stable, and then you see the actual changes that are occurring. So it's a bit of a subtle thing, but it's critically important when you're comparing images over time to calibrate the data and to normalize it as best as possible. This is just an example of other sensors that have been blended together. So we have Planet Scope, Rapid Eye, Planet Scope, Rapid Eye, Planet Scope, kind of a series of data that have all been normalized and brought together. And really this is only possible if you normalize the data to surface reflectance and you're able to correct everything down to surface reflectance. Another key thing, so we're going to talk about the data cube a little bit now. So what we're seeing now is one of the elements of the data cube, which is essentially to create a mosaic of the best images. So on the left, what you see are all of the images available over time, over a specific time period. So you can see that there's clouds and there's images that are completely dark. Some of them are perfectly clear. And on the right, what you see is the best pixel that has the highest NDVI value. So what we do is, you can see the image on the right sort of progressively gets better and better. Now this is showing you the data at 60-meter resolution, and I'm just going to sort of hover with my mouse and show you a place. So I'm going to zoom into this location here. So this little location, I'm going to zoom in now at 10-meter resolution just to give you a sense of what we can do. With the pen sharpening, we can do the same thing. So now I'm zoomed in over the same location, and you can see the resolution I can achieve is much higher. And of course, the data has been mosaicked on the right, and that gives you better product. So before this webinar, we're going to be talking about Fort McMurray through this presentation, and we've been working with some Canadian government organizations that have scientific research interest in these areas, particularly the Canadian Forest Service and the Pacific Forestry Center out in Victoria has been working with us to understand some of these potential changes. So what you're seeing here is, you're going to get a live demo of this in a minute, but what you're seeing here is the result of a comparison of a specific time period from 2017 to what's happened over time before. So we have a query from May to September of 2017, and we're comparing that same seasonal period to the previous year's the same seasonal period. And so what we see are these red areas that appear where there's been a notable change and a loss in NDVI. So the legend isn't displayed, but the red indicates that there's been a severe loss in NDVI over this particular query period. And you can see in this particular location in the middle, this is a pre-cleared area. So this is a surface mining operation in Fort McMurray where the oil sands are located. So at some point, this particular area was deforested, although what we noticed was it went from pre-cleared, so they've removed the forest and they left it with shrubby vegetation where they're planning to expand the mine. And we saw it transform from pre-cleared with residual shrubby vegetation to mine expansion, so converting over to no NDVI because the surface mining operations have occurred. This is interesting. This is a similar pattern that we see over here, and we actually see some flooding occurring just below this area, but we believe this is probably an area where the vegetation or the shrub has been removed and brought up to this location. And up here, what we see is kind of going back further in time, or this is just occurring at a different point in time. The forest is being converted to pre-cleared. So here we're seeing it transform from forest to pre-cleared. So what's really interesting here is, as you'll see in the demonstration, we're able to, set a small extent where we know potentially something has occurred and identify a pattern that we can then repeat on a much larger scale using the Open Data Cube. So we'd like to give a nod to PFC for helping us interpret this earlier today, actually. So thanks very much for that. The analysis ready data, I'll just go into a little bit more detail about analysis ready data. So of course you acquire multi-temporal stacks, we perform image pre-processing, store and manage the open data cube, and then we want to extract the data. I've already mentioned geometric and radiometric normalization being important. We've talked a little bit about this, the value of ARD, so we want to be able to consistently and reliably measure changes on the ground using analysis ready data. And another key point here is shifting the emphasis from pre-processing, which is very time consuming and can be automated through leveraging large compute architecture and automation, to really focus on the important things, which are information extraction. We talked about radiometric corrections, atmospheric correction to get things to surface reflectance. And also the other key thing here with radiometric corrections relates to solar illumination. So things like topographic normalization and BRDF allow us to bring the data to a common point where we can also compare the data over time, taking into account the topographic differences and the solar illumination differences. So we've developed some technology to allow you to do this within our software. So these are some new algorithms that are coming in PCI. So solar and solar view angles is one particular algorithm that's coming. We have another one which is digital numbers to scaled reflectance, so getting the data to a consistently scaled reflectance value so you can compare it over time. We have a spectral pre-classification algorithm that's going to allow you to really sort of speed up and reduce some of the data that you have to work with by identifying where clouds are located, identifying different land cover types and so on to assist with the analysis. Here's an example of the pre-classification. So this is just using the data that's distributed. So we would sort of pan sharpen the data, and then we would perform this spectral pre-classification and store this as a channel in the data set directly, so it would be available to you as a user. This is an example of the topographic normalization. So you see on the left, time of day and latitude at which the data is acquired. This is in southern Africa, so obviously a lot of, depending on the seasonality and the latitude, a lot of shadows occurring on the imagery on the left. And then through correcting for solar view angles and topography, then we're able to normalize the data. And if we're comparing images over time, obviously if you use the data on the left and you're comparing interannual or month to month, those shadows are going to move around, and so you'll probably see changes due to shadows as opposed to changes to things that are occurring on the ground. So it's important to do this as well. In terms of the methodology, we just want to point out some things. So PCI, we have very good metadata handling and information extraction, radiometric correction, geometric correction, cross-sensor calibration. We can pan sharpen the Sentinel-2, as you saw, also the Landsat 8, and preserve that spectral information quality. And the other thing I want to mention, I don't have too many visuals today, but PCI is very strong when it comes to synthetic aperture radar, or SAR, image analysis. And we are developing algorithms to allow you to generate backscatter normalized or average backscatter synthetic aperture radar data, so the equivalent of surface reflectance, so that you can use the radar data to do quantitative analysis over time within the data cube. We do have operational implementation possibilities, both on the desktop and the enterprise and the cloud. As for those of you who know our company, we do have the possibility to scale depending on what you're interested in doing. This is a little bit more of a detailed workflow that shows some of those new algorithms that I just mentioned. So BRDF correction, topographic normalization, solar view. So the blue boxes are all kind of new algorithms that we've added in, and the green ones are ones that we've improved within our software. And these are going to allow you to run analysis-ready data workflows for, as we're showing here, Landsat 8 and Sentinel-2. And that's where we're focusing right now. But because PCI is strong with supporting metadata and adopting support for commercial sensors and other sensors, we can, of course, take the same technology and apply it to other sensors down the road. So we're very excited to expand to the scientific community the types of sensors that can be brought in, because right now primarily it's Sentinel-2 and Landsat 8. So we're excited to bring that capability down the road. So I'm just going to ask a second poll, and I'm going to pass over to Guillaume. So just trying to get a sense of how much imagery the people that are attending today, how much imagery you work with on a regular basis. So is it 0 to 50, 51 to 500, 501 to 5,000, or 5,000 plus? Obviously, depending on your mandate of your organization or access to data or the type of work that you do, this answer will vary quite a bit. It would be interesting to maybe run this poll again in a few years' time once operational data cubes are operational, and hopefully that number is distributed differently. So I'm just going to shut that down in a few seconds. So 3, 2, 1. The distribution is more towards the smaller data sets, and hopefully that over time changes to big data sets. Okay, so at this point, I believe I'm going to pass over to Guillaume.
So hello everybody. So as Kevin mentioned before, we had a collaboration with PSC, and one of the projects was to study an area over Fort McMurray. So what I did is I took all that data and I loaded it into a data cube to see what I could get out of it. So what I'm going to show you right now is basically the CEOS Open Data Cube, which is a very nice interface that goes on top of the data cube and lets you explore your data in many ways. So one nice thing, for example, you can go and take a look at what data you have loaded currently in the data cube. For example, here we see that we have both Landsat 8 and Sentinel-2 data over Fort McMurray. And we're going to use that data to do some analysis. So Landsat loading the Landsat 8 data was fairly easy. I needed to do a little more work to get the Sentinel-2 working, but overall it worked very well. So what we're going to do right now is I'm going to run the algorithm which is called the NDVI anomaly. NDVI anomaly, what it does is basically to a data set, a time period, and going to compare it to previous years and see if there's a significant difference in between those two measurements and flag them on the map. So what I'm going to do is I'm going to take the Sentinel-2 data over Fort McMurray, and I'm going to look for 2017 from period from May to September, and then compare that to the same period in 2016, and we'll see what's going to happen. So, I know. Here you go. So bear with me for a minute. I'm going to input some data. So I'm going to select an area. I know it's interesting. Here you go. So as I said, I'm interested into the time period between May 1st, 2017 and September 31st, 2017. Here you go. And my baseline, which I'm going to compare against, is going to be the same period for the year before that. So from May to September. And I'm going to start running that. So I'm going to do two runs. One is going to be using the pan-sharpened data, and other one's using the unpan-sharpened data over the same area. So one tool that was very useful when I loaded all that data into the cube was the GXL. So GXL is our massive processing tools that let us process a massive amount of data, such as countrywide mosaics. While we developed that tool and created more automation around it, we discovered two very important things. First of all, is metadata is key. You need to have all the information available for you to make informed decision when you do automated processing. And you need to know what has been done to data, what the data means, and all that. The other important thing is you really need well-calibrated data. It's even when you're doing a mosaic, you can compensate for certain effects, but if you're starting with a data set that is clean and a lot less noise, it's much easier to get a better job. And because of those two attributes, we believe that GXL is a very good fit for the data cube, because as Mr. David Lewis stated in his paper, those two, the metadata and calibration are very important, like key elements when using the data cube. So while this is processing, I'm going to show you quickly what the GXL look like. I'm going to keep it very brief. It's not a GXL demo. I'm just going to do. So what I had to do to process the data to be able to pan sharpen it is I had to use data ingest, which is basically a simple process that reads the data from the data provider, converts it to all internal formats, so we can concentrate all the information, all the metadata in one single spot. So as you can see, it's a very simple process. All it asks is for the input folder and an output folder. It's going to read all that metadata, convert it to a PCI disk format, and store it in the output folder. So next steps is to do the pan sharpening process, which again is very simple. It's basically simply an input folder and output folder. And what it does is create a full resolution set containing all the 16 band that are present in the pan sharpen Sentinel-2 product. So that's it. And as I can show you, I run quite a few of those over the time to get all that data processed and loaded into the data cube. So now we can take a look at those results and see what it looks like. So let me load this one up. So what we're seeing on the screen is basically the composite image created by the algorithm. So we're looking at 60 meters. If I look at the difference in NDVI, you can see that there's some anomaly right there and right there. As Kevin mentioned before, those are basically some pretty cleared area that got basically exploited and mined. If you look at the image, it's you kind of see what's happening, but really you have a much clearer picture if you actually take a look at the high-res pan sharpened product, and you can really see the mining going on there. But you do get the same answers that you were having before. So that's it for me. I'm going to pass it back to Kevin. Thank you for your attention. If you have any questions, feel free to ask them.
So thanks, Guillaume, for that demo. Appreciate it. Hopefully that gives everyone a sense of what's possible with the data cube. The amount of data that Guillaume was working with is quite considerable. We were working with somewhere in the order of 230 images total between Landsat 8 and Sentinel-2, and roughly half a terabyte of data. And all of that pre-processing was done on an automated basis using GXL, as Guillaume was showing you there. So just to summarize a few key points, and we'd like to thank once again the Pacific Forestry Center for helping us with this study, this collaborative study that we're working on with Fort McMurray. Just a couple of key things. When we opened up the webinar, we talked about some key requirements for doing Open Data Cube time series analysis. We talked about the need for analysis-ready data, so the need to have super accurate alignment or super registration of images across time, so that when we're looking at the same location over time, when we notice a change, it's not related to the geometric misalignment. And the other key thing is the radiometric normalization, so getting all of the data to surface reflectance measurement so that we can compare actual changes on the ground as opposed to changes in the processing. The other thing we talked about was the Open Data Cube itself, which gives you the ability to scale at a country scale due to its architecture and its the way that it's set up to allow you to work on small areas, but still have all of the data loaded into the data cube. And the third element is what we call multi-temporal analytics. And really what this is once you have your data pre-processed and you're able to have it available in a data cube, what you would like to be doing is to develop your own algorithms or implement algorithms that you're interested in, maybe from another scientific organization, and apply it to your specific data set or geography. And you want to do that in a way that you can sort of test out the results and kind of prototype what kind of information you could get from the data. The way that we see playing a role in this is as follows. So in terms of analysis ready data, we really think there's a good fit with GXL. As you saw in our own experimentation, we leveraged the power of the GXL in terms of parallel computing and automated workflows to allow the ingestion and pen sharpening and preparation of the data so that it could be ingested into the data cube. The middle pillar there is the open data cube. So we, PCI, don't see ourselves developing a data cube. We are really supportive of the efforts being done by Geoscience Australia and now being adopted by CEOS. And we see this as a perfect place to for scientists and organizations around the world to operationalize this concept and make use of this open source code that's available to stand up these cubes. That's certainly what we did. We were able to download the source code and implement it ourselves, and it was quite a nice way to work. The third pillar there is the multi-temporal analytics. And although we don't have an operational tool that can directly talk to the Open Data Cube at the moment, we see Geomatica certainly with its Python API and your ability to script algorithms together in Geomatica and potentially with other software packages, maybe ArcGIS or maybe other open source libraries like SciPy or NumPy or something like that. You could build workflows, implement your specific algorithm, bring those to the data cube to experiment, and then operationalize that. So Geomatica can be one of those tools that can be leveraged for doing that type of multi-temporal analytics. Now, when you talk about implementing this, of course, for those of you who know our company, you will know that our technology is based on a platform. We call it the Geomatica platform, and it has hundreds of algorithms in there. Those algorithms can be deployed in a variety of different ways. They can be implemented within Geomatica, so a single compute environment on a desktop or a powerful computer locally. They could be automated and through Python, and sort of on the higher end, you can certainly achieve high volume production using our GXL infrastructure to parallelize and automate workflows. And of course, depending on budget and throughput requirements and so on, our technology allows you to sort of scale and achieve the operational efficiencies that you're looking for as an organization. So with that, we'd like to thank you very much for attending our webinar today. And if you'd like to reach out and get more information, by all means, contact us, www.pcigeomatics.com, or reach out to us on any of our social media channels. Thanks very much.